Welcome to the concluding part of our study of stoichiometry. In this video, I'll be telling us about normality and about percentage yield. Now, for normality, it is the third way of expressing concentration. You remember that in the previous video, we already saw molarity and molality. But this time, for normality, there's a definition for it. We say that the normality of a solution is the number of equivalents of solutes present in 1 liter of solution. If you'd remember what we said for molarity, we said it is the mass of solute, number of moles rather, of solute present in 1 liter of solution. Number of moles of solute per liter of solution. So in this case, it's not number of moles, it's number of equivalents. So number of equivalents is what we are going to talk about under normality. Now, if you remember the basics of mole, number of moles, it is said that number of moles is given mass over molar mass. But in this case, number of equivalents is given mass over equivalent mass. So it's more like we are saying you could remove equivalent here and put mole, and remove equivalent from there and put mole. So number of mole will be given mass over molar mass. So in like manner, number of equivalents is given mass over equivalent mass. But unlike molar mass that we calculate from formula, equivalent mass or equivalent weight has its own formula. So equivalent weight is molar mass divided by number of reacting units. So based on that, if you were to bring these two formulas together, equivalent mass, which is here, is molar mass over number of reacting units. Then it means that number of equivalents, if not to be written like this, may also be written like this as mass times number of reacting units over molar mass. This is molar mass here, capital M. So I put the meanings of the different terms there. Molar mass is capital M, whereas given mass is small m. So it means also that you may say number of equivalents equals number of moles times number of reacting units, because this is number of reacting units, the small n. Then mass over molar mass is number of moles. So number of moles times number of reacting units will also give you number of equivalents. So number of equivalents, here's our formula. And that same formula can be written like this or written like this, any of them. But for equivalent mass or equivalent weight, it is usually molar mass divided by number of reacting units. So what we're supposed to do next is give meaning to this term, number of reacting units. But just before I give meaning to N, which is number of reacting units, for many questions that we will encounter on normality, the parameters they give us are usually such that we can use this formula to calculate normality. So capital N here stands for normality, and it is calculated as 1,000 times the mass of solute given times the number of reacting units of the solute divided by V. That V is the volume of solution, and that volume of solution is in cm cube. That's why we have the 1,000 there. If I were given a question where volume of solution was brought in dm cube, then I wouldn't need the 1,000. I'll remove it from the formula. But right now I'm leaving the 1,000 there, and I'm assuming that the volume here is in cm cube. Then finally, the capital M there stands for molar mass. So this is the main formula you need for most of your normality questions. But that formula can also be reduced to this. Normality equals molarity times number of reacting units. That is because if you remove this N from this formula you are seeing here, it becomes the formula we saw in the previous video for molarity. So it's very correct to say normality equals molarity times number of reacting units. Now it's time to give meaning to N. What is number of reacting units? Number of reacting units is not as uniform as certain other parameters in meaning. For example, if I say molar mass is the same for different substances. That is, you calculate it the same way. It's the sum of the individual masses of the atoms present in that compound expressed in grams per mole. That's molar mass. But in the case of number of reacting units, its meaning varies for different substances. First, for acids, number of reacting units is the same as basicity. So for an acid like H2SO4, whose basicity is 2, its number of reacting units will be 2. What about HCl? HCl has basicity of 1, so we say its number of reacting units is 1. Then for bases, their acidity is their number of reacting units. So like calcium hydroxide that has acidity of 2 is said to have 2 reacting units. And then finally, for redox, that is reducing and oxidizing agents, we say that the number of reacting units is the number of electrons that they transfer usually during their redox reactions. So for an oxidizing agent like potassium permanganate, KMnO4, during its reactions, it is usually reduced to manganese 2 ion. And if you know how to calculate oxidation numbers, if you calculate the oxidation number of manganese here, you're going to get a +7. So it means that during its reactions, manganese goes from +7 to +2, and that means a gain of how many electrons now? 5. So its number of reacting units will be 5. Consider this other oxidizing agent. We write it as K2Cr2O7. That is potassium heptaoxodichromate 6. Now in this compound, the two chromium ions there, the two chromium atoms rather, are in the +6 oxidation state. And when this compound is reduced, the chromiums usually go to the +3 state. So imagine two guys going from +6 to +3 each. It means that each of them would gain 3 electrons. And that means between them, they are going to gain a total of 6 electrons. So Cr6 plus to Cr3 plus 3 electrons. The other Cr6 plus to Cr3 plus 3 electrons. That means a total of 6 electrons gained. And that means the number of reacting units here will be 6. So based on that, having said that, for oxidizing agents, for reducing agents, it is number of electrons transferred. For acids, it is their basicity, and for bases, it is their acidity. Let's see one question on normality, or better still, let's sneak up on that question by picking a substance. Let's say we pick a substance like H2SO4, which I mentioned earlier. If we were given H2SO4 and somebody asked us, what is its number of reacting units? We'll say number of reacting units is 2. Why 2? Because it's an acid and its basicity is 2. And basicity is number of reacting units for an acid. So number of reacting units is 2. Based on that, see this next one. What if I were asked to calculate the equivalent mass of H2SO4? Very easy. I would say equivalent mass or equivalent weight equals the molar mass, which is 98. How did I get 98? H2 is 2, S is 32, then O4 is 64. 16 by 4, 64. So if you add those up, you get 98. And when you divide that by 2, you get 49. So that 49 is the equivalent mass, and we can write it as grams per equivalent, not grams per mole anymore. We call it grams per equivalent. So the equivalent mass of H2SO4 is 49. So I got that by dividing molar mass by number of reacting units. So what if somebody says that I should calculate the number of equivalents present in 4.9 grams of H2SO4, for example. Take 4.9 grams of H2SO4. How many equivalents will be in it? I could use this formula. I could say number of equivalents is the given mass, 4.9, divided by equivalent mass, the mass of one equivalent, which is 49, according to what we got here. That means 4.9 grams of H2SO4 corresponds to how many equivalents? 0.1 equivalents. And it makes sense because 1 equivalent is 49. 49 divided 10 is 4.9. So if 1 equivalent is 49, what would be 4.9? It's 0.1 equivalent. So the number of equivalents in 4.9 grams is 0.1 equivalent. That's how to calculate number of equivalents, all right? But in the alternative, we said we could use this formula. In that case, I would have calculated number of equivalents in that 4.9 grams as the given mass, 4.9 times N, which is number of reacting units, 2, divide the molecular mass of H2SO4 is 98. If you do this, you still get 0.1 equivalents. You may not bother to use this last one. Why? Because if you were to calculate number of moles first, it will be 4.9 divided 98, which is already here. So when you multiply that by number of reacting units, you still get 0.1. So finally, let's see one question on normality, and let's see how we'll solve it using that our general formula that says normality equals 1000 times mass times what? Number of reacting units divide volume times molar mass. This question says a 400 cm cube solution of HCl was prepared by dissolving 3.65 grams of HCl in water at 36 degrees Celsius. Calculate 1. The molarity, and then 2. The normality of the solution. So see that solution, see that question rather. A 400 cm cube of HCl solution now was prepared by dissolving 3.65 grams of HCl in water at 35 or 36 rather degrees Celsius. Now we have to calculate the molarity as well as the molality of the solution. So if I were to calculate the molarity first, like it says here, molarity equals 1000 times the given mass over what? Volume times molar mass. Easy formula we saw in the previous video. So molarity would be equal to 1000 times, what's the mass of solute here? It's 3.65 grams, so 3.65 divide the volume. The volume of the solution is 400, so I'll put 400 here, and then for the molar mass of HCl, we know it to be 36.5. So working this out gives us molarity at 0.25 moles per dm cube. So the molarity is 0.25 moles per dm cube. Now, how do I get the normality? I could use this very easily, but just before then, this 0.5 moles per dm cube or 25 moles per dm cube, I could write it as 0.25 capital M. That capital M is pronounced molar, unlike the small m that we saw in the previous video, which was molal for molality. So, second part of this question, without wasting time, normality. We say the normality of this will be equal to molarity times number of reacting units. So the molarity is 0.25. Then for number of reacting units, this is HCl we are dealing with, so number of reacting units will be 1, and that leaves our answer as 0.25. But it's no longer molar, instead it's now normal. 0.25 normal. So we pronounce that as normal. So the solution to this question, if you don't want to write it as normal, please, your answer could also be written as 0.25 equivalents per liter. Remember, that was the definition we gave to normality. We said it is the number of equivalents of a solute present in 1 liter of solution. So equivalence per liter is the same as normal, just as mole per liter is the same as molar. So in this case, interestingly, the molarity is the normality. But is that always the case? No. If I had changed this to maybe H2SO4, then after getting molarity, here would have multiplied it by 2, which is the number of reacting units of H2SO4. So that's it for normality. You look for more questions to solve on this, and as long as you apply the basic principles we have outlined, you have no issues. So at this point, let's turn our attention to percentage yield. What is percentage yield? And how is it calculated? When we prepared for exams before now, one mindset that some of us tried to build was this mindset of aim high. So in the end, if you are not able to hit your target, at least you go very up high, close to it. So in that case, some persons may target to score something like 9 out of 10. That's your target now. But after the exam, you may score 7 out of 9, or let's say 6 out of 10, please. So in that case, 9 out of 10 is your expectation. Maybe after the exam, thinking of how many you got right, how many you failed, okay, by your mathematics, you are expecting 9 out of 10. But when the results are released, you see 6 out of 10. In that case, 9 becomes your expected score. It is what you calculated to be your score. But 6 is your actual score. So if we were asked in that case for the percentage of the final score that you got, which is like your percentage success or percentage pass, you may say it is 6 out of the 9 you expected, which is your actual score over your expected score or your calculated score times 100, because it says percentage, right? So the percentage of the score, your calculated score that you actually got, the percentage of the calculated that came to reality that you actually got was 6 out of the 9 you calculated times 100. So without wasting time, straight to percentage yield. Percentage yield tells us certain things about a reaction. More importantly, it tells us how well the actual yield of that reaction resembles or matches our expectations. And usually, reactions tend to yield less than we expect them to yield. That is, the actual yield from a reaction is usually less than what the yield is expected to be. So the percentage yield is usually calculated as actual yield over expected or calculated or theoretical yield. That's another term for the expected yield. We call it the theoretical yield or the calculated yield. And then you multiply those by 100. So this is what we refer to as percentage yield. That's the formula we use for it. So consider a question like this one. Consider this question that says, when 3.25 grams of zinc was reacted with excess dilute HCl, 0.02 liters, well, let's say 0.2 or 0.02, no problems, liters of hydrogen gas was evolved. Full stop. What is the percentage yield of this reaction? Then you are given zinc as 65, H as 1, and Cl as 35.5. Beautiful. See this reaction. When 3.25 grams of zinc was reacted with excess dilute HCl, 0.02 liters of hydrogen was evolved. Now we are asked for the percentage yield of this process. This amount given here, this volume of hydrogen that was evolved, was what actually happened. They said when they carried out the reaction, this happened. But what do we expect from the principles of chemistry? What do we expect to happen during this reaction? Our normal stoichiometry will tell us like this. According to what we know from basics, zinc will react with HCl as follows. This is zinc plus HCl to give zinc chloride plus hydrogen. This equation says that 1 mole of zinc would normally give 1 mole of hydrogen, right? Then, the zinc in the question, if you remember our first video on stoichiometry, we talked about the language of the equation as opposed to the language of the question. So the equation would always bring the language of mole. But in this question, zinc is in grams. So how do I change this 1 mole to gram? It's given to me right here. So in place of 1 mole here, I'm going to write 65 grams, right? Then beyond that, for the hydrogen in the question is in liters. That wasn't given to me here, but I know that 1 liter of a gas at STP, that wasn't mentioned as well, is 22.4 liters. So 1 mole of a gas, like hydrogen, at STP, so I'm assuming standard conditions here, 1 mole of hydrogen is 22.4 liters. So it means that 65 grams of zinc would give 22.4 liters of hydrogen. That is standard. That's according to the equation. The 1 mole in the equation are the things I have expressed alternatively. So what is left now is for me to ask myself, if 65 grams of zinc will produce this volume of hydrogen, what about 3.25 grams of zinc? What would it give there? To do that, I'll put 3.25 here, grams, and that becomes x liters. So that my x becomes 3.25 times 22.4 divide 65. Now if this were to go there, like we say, you get 20. Yeah, 3.25 times 20 gives you this. And it means therefore that your 2.24 would have to be divided by 20 as well, and that gives us 1.12. 22.4 divided 20 is 1.12 liters. So if you use your calculator, you are going to get 1.12 as your x. So it means therefore that with 3.25 grams of zinc, what we expect of hydrogen is 1.12 liters. So that is what we call the expected yield or theoretical yield or calculated yield. But in real life, what did they obtain? Just 0.02 liters. That's very low. So I'm going to say now, percentage yield for this reaction equals the actual yield, which you will always be given. If you are not given that, then you'll be given the expected. But it will be strange that you are asked to calculate actual yield, except you are given expected and you are given percentage yield. Otherwise, the way it typically comes is you are given the actual yield, you are expected to calculate the theoretical yield. That's where your work really lies, and then you get your percentage yield finally like this. The actual yield in the question, 0.02, divide the theoretical yield, 1.12, times 100. Now for that, I'll need my calculator. So that becomes 2 divide 1.12, and that gives me 1.79%. That's ridiculously low. So we have 1.79% as the percentage yield. And I can imagine that a reaction were to give us this yield, it wouldn't be worth it at all. It would just be a waste of reactants. So typically, percentage yield values are high. But we don't go into the exam with that mindset, because you could be given a question that is, just quickly put up like this one. I put up this question very quickly, like it has existed anywhere before, I believe. But I put it up very quickly, and yes, we have an answer. What is more important is the principles. Understand the principles, understand that what you have been given here is actual yield. What you will calculate is theoretical. Then from there you can get your percentage yield as actual over theoretical or expected times 100, like I have done here, and you leave your answer this way in percentage. So that's it for normality and theoretical actual yield, percentage yield, and that's it for stoichiometry. So it is my hope that after watching these videos on stoichiometry, the other parts of general or inorganic chemistry that would depend on a sound knowledge of this part will become very easy for you. Thanks for watching, but remember, you need to share, you need to like, you need to subscribe. Let your friends hear about this channel and you'll be doing them plenty good. I'll see us in the next video.